Hi everyone, I'm Ryan Shi, and I'm a second-year PhD student in societal computing at CMU, and also the co-organizer of this event. And I'm gonna talk about our project on improving efficiency of volunteer-based food rescue operations. So this is a collaboration with CMU undergrads Ewan and Kimberly, and Leah at 412 Food Rescue, which is a local Pittsburgh nonprofit, and my advisor Faye. So food waste and food insecurity are two very important problems that coexist in many parts of the world. And take US as an example. According to the 2018 data, 11.8% of the Americans are living under some sort of food insecurity. And we all know that under this current pandemic, that number is only going to go up. And at the same time, an average American wastes about 1 pound of food every day. And that leads to roughly a quarter of the food produced in the States going to waste. So clearly this simultaneous shortage and waste is problematic. And many community organizations have stepped up to mitigate this problem. So traditionally, most of these community organizations are food banks. These food banks receive donations, and then they match these donations with recipient organizations, and then they deliver the food to those organizations. So typically in the literature, this is studied as a matching problem or a vehicle routing problem. But in recent years, there's a new type of food rescue that start to rely on external volunteers to do the transportation. And as we show in the slide, here's what a particular food rescue will look like to a volunteer. Like, imagine you are the volunteer here, you will have a smartphone with an app installed on it. You will get a push notification if some food rescue shows up, and then you can choose to claim it. And then this app will tell you where to get the food and where to deliver. So then you just drive to pick up the food from the donor and then deliver it to the recipient organization. Well, so the first time I got introduced to our collaborating partner, I thought, this was such a brilliant idea. These nonprofits like Food Rescue, they don't have so much budget. They don't own so many trucks and employees to transport the food. So now we outsource this to volunteers, and suddenly, like, problem solved. But that's not quite. There's no free lunch. And I spent a couple of days at their organization and sort of realized, there's still a couple of drawbacks to this paradigm of operation. The first thing is, now we rely on volunteers to complete the rescue. We don't know really whether a rescue will be claimed by any volunteer, or like even when it will be claimed. Like, you don't want a food rescue to sit there for like 8 hours without anyone claim it. And the second thing is, so having volunteers to do the job, doesn't mean that the food rescue, like the human dispatcher at the food rescue organization, doesn't mean that they can sit back and relax once a rescue is published. These human dispatchers need to attentively monitor whether a rescue has been claimed and deal with all kinds of volunteer incidents in real time. And as I have some personal experience with that, I can promise you that is a really demanding job. The human attention here is a scarce resource that needs to be allocated more intelligently. So here's our contributions. The first thing is we build a predictive model of whether a rescue will be claimed. So the dispatcher will have a better idea of which rescues might not work out so that they can better plan for that. And the second thing is we also did a data-driven optimization to advise the dispatcher when they should send smartphone notifications, when they should intervene personally, and so on and so forth, so that we can better allocate their effort. So let's focus on our first task here. The first task is to predict whether a rescue will be claimed or not. Well, there seems to be something weird with the slides, but it doesn't really matter. So by analyzing the data, we discovered that the claim rate, whether a rescue will be claimed, is highly correlated with three things, basically: the timing, the weather, and the location of the rescue. So for example, we see on this map of Pittsburgh, like the claim rate really differs wildly from zip code region to zip code region. But also because these zip code regions are really different in terms of their size and shape, in practice, we use these grid cells to divide up the area of Pittsburgh. And in fact, completely what actually matters here is the number of active volunteers that are in each grid cell. And timing also matters here. And for example, like whether a rescue happens on a weekend or a weekday or like evening after the work hours or not, that also matters a lot. And also like the weather of the rescue, as you can imagine. So after we gather all these relevant features, we want to do this prediction task. And we do that by using a stacking model. So how the stacking model works is that you have your training data and you divide your training data into two parts. As you can see on the slides, we have DA and DB, these two parts of the training data. We will use the first part of this data, DA, to train some weak learners. And in this case, we have five different Gaussian classifiers and a random forest. You train that, and then you use these trained models to do prediction on your second batch of training data, the DB here. The output of these predictions will be sent to train a meta-learner, in this case, is the multi-layer perceptron, which will give us the final output of the model. And we compare this performance with a few baselines, including like GBM and random forest, Gaussian processes, and so on. So we see that with the stacking model, we actually have a perfect precision. And why precision matters here in the food rescue operation is that it characterizes when a rescue is in fact missed, but we predict it as being claimed. So that's especially important because we don't want a rescue to go missed without having the dispatcher's attention, because that basically harms the motivation from all parties involved in this. And I won't have time to introduce our second contribution, which is the optimizing the intervention and notification scheme. And if you're interested, we can discuss offline, and you can also find the details of all these results in our full paper. So with that, I would like to say special thanks to our collaborators at Forum to Food Rescue, especially Leah, Jake, Alonso, and Ryan, who we've been working very closely with for over a year, and also many others in their great team. And especially, during this hard time, when many businesses are shutting down and people are losing their job, these organizations, the food rescue organizations, they are still operating, and they are still helping the communities that need them the most. And that's it. And I'm happy to take any questions or comments. And the full paper was published at AAI 20 this year, and it's also available on my website. Thank you.
Great. So any questions from the audience? Yeah. Sorry. I accidentally lowered someone's hand. Do you want to? Yeah, thanks, Marish.
Yeah. So hi, am I audible?
Yeah.
Yeah. So hi, Ren. That was a great talk. I had a question. Like, since you are using a stacking model and that already includes random forest and gradient boosting in it, so its accuracy should be greater than that. So is it like a convention that since you are already using those models, so your accuracy should be better than those models?
That's a great point. Actually, yes, that's right. Like, indeed, when in the stacking model, we're using some weak learners that we use as a comparison of baselines.
Yeah.
But I think in our original work, we also had some comparison with like different ensembles of these weak learners.
Okay. It would be great, like if you could post the link in the chat for your paper.
Yeah, sure. I'll post that link right after I stop.
Okay. Thank you.
Thank you.
Cool. Thank you again.